Hi, this is Tor Lacey with a lecture about earthquakes. Here are the main learning objectives for this lecture. An earthquake could be defined as the vibration of the ground from the waves of energy released when a fault breaks. Faults form where stresses acting on the crust cause brittle deformation. Typically, movement along the fractures happens intermittently in sudden bursts, which might be separated by hundreds or thousands of years. Faults break or rupture when the pent-up strain in the rock on either side of the fault overcomes the frictional resistance that was preventing movement along the fault. This allows the elastically strained rock on either side to snap back into position, and through doing so, the stored energy is released as seismic waves, which travel outward in all directions from the focus. The focus, also called the hypocenter, is where the fault first ruptures. The location on Earth's surface directly above the focus is the epicenter. The epicenter is a more useful way to refer to the origin of the earthquake, since it's on the surface and can therefore be plotted on a map. To summarize how an earthquake happens, first, tectonic stresses cause brittle deformation of the crust. Second, friction along the fault leads to a buildup of elastic strain. 3. Strain accumulates until friction is overcome and the fault breaks. 4. Fault breaks at the focus. And finally at 5, the crust snaps back into position. Elastic rebound. The locations of earthquake epicenters creates linear patterns when plotted on a map of Earth's surface. Earthquakes can happen any place on Earth where stresses are acting on the crust, but especially along plate boundaries, as we see by patterns made by epicenter locations. The pattern isn't perfect, however, because earthquakes can happen away from plate boundaries as well, although these happen less frequently. As you may know from experience, when we have an earthquake, reporters will usually talk about the epicenter of the earthquake. But how do we know where that was? Is this something that can be directly observed? Is there some sort of physical evidence on the ground telling us where the epicenter was? Not necessarily. Instead, we have to, in a sense, work backwards from where the shaking was recorded to determine where the shaking came from. This is part of the art of seismology. In order to do this, seismologists, geologists who specialize in the study of earthquakes, use a tool called a seismometer. As earthquake waves pass through the ground supporting the seismometer, the machine moves with the ground, recording the shaking. The more intense the energy passing through, the greater the shaking, which will be reflected in the seismogram, the record of the earthquake as recorded by the seismograph. This is an example of a typical seismogram recording, which reveals that not all seismic waves are the same. The energy produced by an earthquake moves in different ways and at different velocities. Primary, or P waves, travel the fastest, and therefore arrive at a seismogram first. P waves typically cause the least shaking, which is reflected in their lowest amplitude. The secondary, or S waves, arrive at the seismogram second because they are slower. They shake the ground horizontally in a side-to-side motion and typically have moderate amplitudes. Surface waves arrive last, as they are the slowest, but have the greatest amplitude, and therefore can be the most damaging to structures. They move the ground with a shaking motion or a rolling motion, and therefore have two names, L waves and R waves. For locating the epicenter of an earthquake, we utilize the fact that P and S waves travel at different but constant velocities. As an analogy, imagine you are always driving 100 miles per hour and your friend always 50 miles per hour. If you arrive at a destination 1 hour before your friend, how far have you driven? 100 miles, because at 100 miles, your friend has only traveled 50 miles and will need 1 more hour to travel the next 50 miles of this 100 miles trip. The difference in arrival time between you and your friend, or in the case of seismology, the P and the S wave, is called the lag time. By studying a seismogram, the lag time is easily measured and is what is used by geologists to determine the distance the seismogram is from the epicenter of an earthquake. First off, we need to consider the scale of the seismogram. Then measure the distance between the first P wave and the first S wave. This gives us the difference in arrival time between the two waves at a seismograph and our lag time. The lag time is then plotted on a travel time curve for the velocities of seismic waves as a function of lag time and distance to the epicenter. A travel time graph gives us a distance to the epicenter based on the difference in arrival time or lag time of the P and S waves at a seismograph. For example, if the lag time was 5.5 minutes, 1, 2, 3, 4, 5 minutes and 30 seconds, then the seismograph that recorded the earthquake was 4,400 miles from the epicenter. While the travel time graph gives us the distance to the epicenter of the earthquake, it does not give us a direction to the epicenter. In order to pinpoint the location of the epicenter, a compass is used to draw a circle around the position of the seismograph with a radius equal to the distance to the epicenter. In this way, all possible directions are accounted for. When this is done for 3 or more seismograph localities, a process called triangulating, the circles will intersect at a point representing the epicenter. The Richter magnitude scale is probably the most well-known technique for measuring earthquakes. It uses the seismogram record to quickly measure the intensity of shaking. A more accurate measure of earthquake intensity, especially for larger quakes, is the moment magnitude scale. With more accuracy comes more measurements and complex calculations than the Richter scale, making a magnitude calculation more time-consuming. Consequently, earthquakes are typically reported to the public based on a quick estimate of the magnitude using the Richter scale. The amount of damage caused by an earthquake at a particular location depends on several factors. The intensity of the shaking, the greater the magnitude of the seismic waves, the more intense the shaking, the proximity of the location from the focus and epicenter. Seismic waves weaken with distance, so the closer, the more intense the shaking. The geologic conditions at the location. Loose sediment will experience more intense shaking than solid bedrock, and shallow groundwater can lead to liquefaction. And material and design of buildings and other structures. In Haiti, for example, poorly constructed buildings collapsed, causing the deaths of tens of thousands of people. Liquefaction happens where there is loose, porous sediment and a shallow groundwater table. If the sediment is shaken with enough intensity, it compacts under its own weight, forcing the groundwater to the surface, where it saturates and liquefies the sediment. Tsunamis are rare, but can be extraordinarily destructive. In Southeast Asia and Japan, hundreds of thousands of people were killed by tsunamis triggered by the 2005 Indonesia and 2011 Japan earthquakes. A tsunami wave can be triggered when a fault intersecting the seafloor suddenly slips, disrupting the ocean surface, which creates a very long, fast-moving wave. Because the wavelength is so long, a single wave contains a huge volume of water, with a huge mass and momentum that can easily destroy structures and kill people. If you've grown up in Southern California, you know that we're waiting for the big one. A devastating, strong earthquake caused by slippage along the San Andreas Fault. According to the USGS, the probability of a major earthquake in the next 30 years is 60% for an earthquake measuring magnitude 6.7, 46% for a magnitude 7 earthquake, and 31% for a 7.5 magnitude quake. To put it another way, the recurrence interval for an earthquake along the San Andreas Fault in Southern California was recently recalculated to about 100 years. Considering that the last big one on the San Andreas Fault in Southern California was the 1857 Fort Tejon earthquake, we are very much overdue. This map shows how intensely the shaking was felt in California, Nevada, and Arizona during the 1857 quake. The Roman numerals refer to how the shaking was felt by people according to the modified Mercalli scale. So now that I've got your attention and hopefully not scared you too much, what can you do to be prepared for an earthquake? Plan. Make a plan with your family. Make a plan with your neighbors. Make a survival kit and include, at the bare minimum, the following. Water, 1 gallon per person per day. A 2-week supply is recommended. Water for your pets. Canned and packaged foods, enough for several days, and mechanical can opener. Extra food for pets if necessary. Medications, fire extinguisher, crescent and pipe wrenches to turn off gas and water supplies. First aid kit and handbook, flashlights with extra bulbs and batteries, portable radio with extra batteries, waterproof, heavy-duty plastic bags for waste disposal. Finally, be informed, because it's not a matter of if, but when. This brings us to the end of this discussion about earthquakes and their consequences. Thank you for listening.